Hello everyone and welcome to this section. In this section we're going to train a simple perceptron network that we actually built before, and we're going to see how can assess the performance of our network. Okay, all right, so again I'm going to walk you through a quick overview of what we have had before. Again, all these codes up to this moment, this step, basically we have done it before. I'm just going to go through it. We're going to import all our libraries. So that's the first step. So let's run it. And then the next step is that we're gonna load the data. All right, so we loaded the data. We actually took a look at the data. So we have again our two inputs and our speed, which is our target class. And then we plotted the data here, as you guys can see. How can we decide, if the truck we're gonna drive, fast or slow? Let's keep going. Here again, we loaded, the X train. So X train has two columns, right? And then we have again Y train as well, which is only have one column. All right. And then the next step is that we started to build our network. So we build just one single neuron network. So we have two inputs and we have one neuron, right? So here we have our input dimensions is 2, our activation function is sigmoid, and we did what we call it the dense to add, the network in a sequential form, a sequential way. Okay, so up to this moment, we actually discussed it. Here, okay, let's add these two lines that can be used for training. So what we do afterwards, we do what we call it model, compile, and then we use the loss function, okay, which we'll call it binary cross entropy. We use binary cross entropy because we only have, one output that has a binary value, either 0 or 1, okay? There's binary categorical, for example, entropy. We're gonna use it moving forward if we have different categories, for example, and so on, okay? Okay, so here we're just gonna use the binary cross entropy as a loss function. And then the next one, we're gonna use the optimizer, gonna be Adam optimizer. Again, I tried to copy a couple of, you guys can go ahead and search for Adam optimizer, but Adam is kind of a specialized form of our backpropagation. It relies on the backpropagation the same way or the same fashion. Again, it calculates the gradient, and it does what we call a gradient descent algorithm to train the network, but it's a kind of specialized form, okay? I'm not gonna go again into the details of the Adam optimizer, but it's very powerful optimizer that we can use to train our artificial neural network, okay? So that's pretty much it. The next step is we're gonna do model.fit, which is this command. And then we're gonna use, okay, first of all, what our training data. So we have our X train, that's our training data. And we have our target class, which is Y train. And then we're gonna specify how many number of epochs. So we have 100 epochs. And here verbose, which is how many, what details we wanna plot as we go, okay, as we start training, okay? And that's pretty much how can you fit or how can you train our network in a nutshell. Obviously behind all of this, there's a lot of mathematics, a lot of equations, a lot of stuff in the background. But the whole idea is, as we mentioned before, the intuition. We have input, we have output, we calculate the error, we go back, we update the weights in a certain fashion. All right, let's run this. And actually the model is running. As you guys can see here, these are the number of epochs that we showed you, which is how many times we actually show the training data, and we'll go back and update the weights. As you guys can see, the loss is going down. This is going down. We reach let's say 0.28. Okay. All right. Let's take a look again at the model summary. We showed that before. So we have 3 tunable parameters, 2 weights, and 1 bias. All right. And the next step is that, okay, now our network is fine. Okay. Let's go and predict, or let's assess, for example, the accuracy of our training data, okay? The key element here is that we didn't divide the data into training and testing, all right? This is, again, a very simple example. We didn't do any divide. We used the entire data to train, and here we want to assess the actual training as well, using the exact same training data. In general, I don't want you guys to be confused. This is just a very simple example, okay, using one neuron, just to show you how can we build something from scratch. Moving forward, the next exercise, actually we're gonna take the data, we can go do the right thing. We're gonna, first of all, develop a multi-layer perceptron network, and we can actually take the data, divide into train and test. Here, it's a very simple, plain example. We use the exact same data. We didn't even divide it at all. And that's, just to give you if you guys not familiar with Python, if you're not familiar with programming in general, I don't want to show everything at once. Here we're just gonna build it step by step. So here what we're gonna do is we're gonna do model, okay, which is our trained model right now. We're gonna use what we call it predict classes, and we're gonna use the X train. Okay, so let's predict. So simply here you are doing a forward run through the network, and the network will give me its prediction, which is Y train predict. All right, okay, let's run it. Okay, that's good. All right, so the next step is that we wanted to, okay, let's assess the performance of our network just for the training data set. So what we're going to do is that we're going to use from sklearn, okay, we're going to use the metrics, all right, and within that matrix, we're going to import what we call confusion matrix. If you guys recall, we discussed the confusion matrix before. It's again one-stop shop that can show us all the correctly classified samples and all the misclassified samples. And then what we do is that we call confusion matrix, and then we pass along our ytrain, which is simply our true labels, and our prediction, which is ytrain predict. Okay, the confusion matrix will return CM, and then we're going to use the Seaborn heat map method within the Seaborn library to actually plot again the CM, okay, which is our confusion matrix, and then annotation true, which can be used to actually plot the number, the total number of classes within the confusion matrix. And let's get started. Let's run it. Let's see what's going to happen. All right, actually looks pretty interesting. So here, as you guys recall, we had 1,000 samples, and here the network has correctly classified 500 here. Okay, the class was 0, the true class was, the prediction was 0, and the true class was 0, which is good. And then the network correctly classified 498 samples as well. However, it misclassifies 2 samples. Okay, that's basically the error that we've got out of this network. Okay, that's pretty much how can you view the confusion matrix. The only problem here, obviously, this is kind of, you know, type 2 error. Okay, and we try to avoid type 2 error at all costs, as we mentioned before. But again, this is kind of like a very simple example, and we didn't even run, we didn't even use the testing data set, and we didn't even run any advanced, you know, multi-layer perceptron network. Okay. The next step to visualize the results is to kind of use kind of what we call it a mesh grid to visualize the results. Again, it's kind of, you know, if you guys don't even want to like go through all that code or write that code, you can again utilize it or use it, you know, whenever you want to just to show you a visual representation of, okay, these are the 2 classes. Where did we draw our decision boundary, or where did we draw our, you know, kind of line that you know, like separates the 2 classes together. Okay. So what we did here is we're going to create kind of a grid. So they're going to create what we call the mesh grid, all right? And what we're going to do is that we're going to get kind of a grid using the data, the X training data that we have. So here we just define the start point, the stop point, all right? And that will return again. We're going to do that as well for the second step here too as well, all right? And that will create our kind of mesh grid for our 2 samples, for our 2 inputs, which is X1 and X2. Okay, since we have 2 inputs, that's why we have done it kind of, you know, for 2 inputs. And then next, we actually do the actual prediction. So that will actually give us my prediction. These are predicted values. Okay, and why? Because we want to show the actual true values along with the predictions as well on one graph. All right. That contour F will simply plot our contour. I'm going to show you as well how does it work. And then here we just want to specify the color maps to red and green, which is, you know, kind of to show us, okay, how many samples were truly classified and how many samples were misclassified. And then we limit simply the x-axis and y-axis to the minimum and maximum values of x1 and x2, which is our 2 inputs. And then afterwards, we actually do use a scatter function, okay, which is plot.scatter, to actually tell us, okay, where are the true values and where there are or the correctly classified samples and misclassified samples. All right. So let's take a look and let's run it. And that's that's very interesting. So as you guys can see here, that's my first class and that's my second class. And you guys can see that's kind of the boundary that we had in between. Okay. Which means that the network, even with just one layer, with just one neuron, was able to adjust the weights in a way to draw that boundary and classify the 2 classes. Again, this example is very simple, very easy. Moving forward, we're going to have way more complex and way more complicated examples. All right. Okay. The next step is, okay, let's view the weights and let's view the biases. As we have done before, we have done it before for an initialized weights and biases that, you know, weren't trained. Now we actually have a trained network. So obviously we'll see different numbers. So if we run the weights and we run the biases, you will get different numbers. The bias, if you guys recall before, was 0. Here actually the network had to adjust the bias to 2.2. Here we have the weight 1 minus 3.2, weight 2 minus 2.1. And pretty much if you guys think about it, if we assume that, let's say, our activation function is in a way like linear form in a way, okay, it's kind of the equation of or the model of that line in simple form. we have two weights and we have a bias. It's very simple equation, linear equation that can tell us, okay, that's the equation of a straight line. You can use it, for example, using regression, but here we actually use an artificial neural network, which is, kind of an overkill here in this example. But again, we use just one neuron to classify these two classes. All right, that's pretty much all what I have for this section. I hope you guys enjoyed it, and see you in the next section.